Okay, well, welcome back to the second part. Now, this one, we'll try to keep it down, hopefully around 10 minutes, and then we'll complete the remainder of the lesson tomorrow in class. I just don't want to take up too much of our time together in problem solving. So we'll do our best to keep it short. Okay, so we're going to move into the concept of what we call vector projections. And actually, through the concept of work, you've already seen a vector projection. The best way that I can think of explaining it is if you think of the concept of a shadow. Okay, so if you look at the diagram that's here, let's just consider that this is, our sun, and that the sun's rays are beating down directly. Okay, as far as direction is concerned, are beating down in this direction here. Now, if you were asked, does vector v have a shadow? I'm sure you'd say, yeah, of course it does. Well, the next thing I would want to ask you is, well, just exactly where does that shadow fall? How long is it? What is its magnitude? Okay, so what we'll do is let's just kind of diagram this a little bit more. If we were to draw in a perpendicular, okay, to where V is, if we were also to take V, which is about, that long, I'm just going to change the color of this vector, nice bright red, and if I took that vector and translated it down, as without changing its length, I would simply have moved vector V through angle theta, right? I'm simply taking the vector V, moving it through angle theta until it overlaps vector U, until it projects onto the vector U. Now, as far as shadows concerned, you and I both know very well that if the sun's rays are directly overhead, that this vector that we've projected onto U is a bit too long. In fact, the shadow should be, that long. So let me just take that out, okay? Because we're not projecting all of V onto U. In fact, there's only a certain component that's being projected, okay? So in fact, what are we doing? We are taking the vector V, okay, its magnitude, and we are multiplying it by the cosine of angle theta. Okay, think back to when we did the work example. That vector that we projected was f cos theta, right? It was the horizontal component to the force vector. Here, again, similarly related, we have the component, the horizontal component of vector v. Okay, we call the shadow the projection, literally the projection of the vector v on to the vector u, and it is equal to the magnitude of v multiplied by cos theta. Okay, the question bubble that I have down here was simply to get you thinking about where have we seen this concept before, and as mentioned through this talk, it is when we were working with the work. Okay, moving forward, so far we have calculated the magnitude of the projection of V onto U. It's also known as the scalar component. Okay, there is one thing we're lacking. That is, if you look back at what I've drawn, okay, this here is a vector. This is the notation for that vector. But vectors, they don't just have magnitude, which you can see here. We know that vectors have direction. So we are lacking direction. So the direction of the projection of v onto u needs to be the same as that of vector u. So we need to do some things here. If we're going to give direction to the scalar component, then we need to multiply the magnitude by a vector. And not just any vector, but by a unit vector that is in the same direction as u. So let's see what that's going to look like. Let's just say that the vector u, and not specifically u, let's say ku, okay, a scalar multiple of u is the unit vector we're searching for. It's not u, it can't be u, but it's going to be something else. Let's call it ku, and that's going to be the unit vector. So the magnitude of the vector would be this expression here. Now we do know that we'd like to solve for the value of k, because if we know what k is, then we will have the direction of our vector. Okay? So we'll come back and review that in a moment. So what we can do is we can take that multiple out and take its magnitude. We can multiply that by the magnitude of vector u, and that is going to be equal to 1. In solving this, we can see that k is then going to be 1 over u. That is the magnitude of the vector u. Okay. Now because k, or the vector, unit vector, is in the direction of u, we know that our k must be positive. So therefore, the value of k is 1 over u. Okay? So far so good. We now have the direction of the unit vector. We just don't have a representation for the unit vector. So what this means then, I'm going to change colors here just to differentiate between what's been written so far. So from this, the unit vector that we're looking for, okay, is going to be ku, of course, right? But we have determined that k is 1 over the magnitude of u. And that's multiplied by vector u. So let's just be clear about a couple of things, and that is to say, this is the vector u, but this here, okay, is the direction of our unit vector, okay? So what that means is when we go down and have a look at our formula, let's study the parts of this, okay? So this portion here, this gave us, as you saw before, the magnitude of the projection. And now this portion here is going to give us the direction of that projected vector v onto u. Okay? And I'm recognizing that my formula needs a couple absolute value bars, so please add those in. Now we're up to about 9 minutes or so. We're almost at the 10-minute mark. I'm just going to look forward to see what it is that we're accomplishing next. And at this point in time, well, I guess we'll just end it off here. When we return to class tomorrow, we'll continue with a little bit more, and I'll leave you with this closing bit. Oh, it looks like my media file is not going to work. All right, we'll just close that down then. Anyways, that's the end of this particular podcast. When you return to class tomorrow, we'll cover just a little bit more.